welcome back, friends. This is going to be our seventh session of today's event, and the session will be on distinct count for Power BI, which will be delivered by Philip Seamark from New Zealand, who is also a principal program manager at Microsoft. Philip has over 25 years of vast experience in Microsoft BI stack, data warehousing, and enterprise data modeling. So Philip, the floor is yours now. You can start the session. And friends, please remember your questions should be posted in the Q&A panel and not in the chat window. Philip will be answering the questions post the 60 minutes allotted time for the session. Thank you so much.
Cool. Thank you for that kind introduction, and hello to everyone. Thank you very much for joining my session today. As mentioned in the topic, we're going to be talking about the distinct count calculation for Power BI. And before I start, let me share my screen. And hopefully you can see that.
Yes, Philip.
Distinct count for Power BI. Okay, so yes. So my name is Phil Seamark. I work for Microsoft. I work on the Power BI team for Microsoft, in particular a specific team called the Customer Advisory Team, which we often call the CAT team. My role in this team is as a principal program manager, and I do spend quite a lot of time working with large enterprise customers, helping them work through challenges and helping them optimize their often very large and very complicated models. So I get exposed to some very interesting scenarios, and sessions like today are my opportunity to share what I've learned with you to hopefully allow you to build better models and make better use of Power BI. So the agenda today, we'll just quickly run through this. So we're going to focus a little bit on why the distinct calculation in particular is different from other calculations, because it's very important to understand this. And I want to run through some exercises which hopefully will help you understand this. We're going to look at different options for ways that you can write distinct count. Often these have different pros and cons, and we'll just focus on a couple of really useful patterns that are good options to go through. And I've got a couple of demos on that. Lastly, I'm going to touch on a concept called approximate distinct count, which can often be quite a useful technique to apply, especially when you've got a lot of data and you want to really have aggressive runtime for your queries. And then we'll recap with a bit of a summary. So, as I mentioned, my role in the CAT team with Microsoft, I quite often spend time with large enterprise customers, and it's not unusual for them to show me a report to say, hey, this is running really slow. And when I dive down into it and start having a look at the components of the report, I discover that there's a heavy use of distinct count calculations within that report. Now, distinct count is a perfectly useful metric for BI reports, but it's often a bit of a mystery and a puzzle to why reports with distinct count being involved will take longer to run and load than perhaps other calculations which on the surface also appear to be potentially quite slow, such as average, mean, max, even just sum. Why is distinct count necessarily that much heavier on your system? So what I thought I'd try and do is describe using playing cards, exactly what the system needs to do when it needs to do some calculations such as distinct count. So this is why is distinct count different? So just imagine you had a set of playing cards from multiple packs of cards, and you shuffle them up, and you do quite a good shuffling of this, and you want to perform a variety of calculation types. And you'll notice here, I have 2 5 of clubs. I've got a 3 of spades, 5 of club, etc. And we're going to walk through step by step how each calculation type approaches their goal, and we'll see how that goes. So we're going to start with a sum calculation. So we're going to show with playing cards exactly what's required of your BI engine to arrive at the result, which is the sum total of the numbers on each of these playing cards. So first of all, we start with the first one, the first card, and we bring it down, and we can see that the value is 5. So what we're going to do is we're going to allocate a single piece of memory and store the value of 5 in that memory, that piece of memory, and nothing more. And then what we can do is we can discard that number 5 card, playing card, and go and grab the next card from the pile. And in this case, we're getting the value of 3. So what we can do is we can add the value of 3 to the value that we had previously stored. So we're not going to keep the old value. We're just simply going to accumulate this number, and then we're ready to discard that card and bring on the next one. So 8 plus 9 equals 17. Again, we're not using much memory here. We're just accumulating the value, and we're going to throw away the 9 card and bring down the number 7. We increment our single value that we're storing, and then finally we bring down the last card in our pack, which is our 5 of clubs again. So to complete the calculation, we arrive at a value of 29, which is the correct value. But we only needed to do one pass through the cards. We didn't need to sort the cards. The cards could have just been picked in any order, and this is quite an important thing to remember, because sorting adds an extra overhead to any exercise that we might need to do. We only needed to increment a single value. So think of this as how much memory is required by the engine to complete this operation. There was no need to keep track of the number of cards read either. We didn't need to have a second piece of memory keeping track of how many cards we've read. It just really doesn't matter. It's not important. We can just fly through the cards. What's also important is that we can derive subtotals and totals very easily. So if we were to apply some grouping over this, which I'll drill down on a little later, when it comes to subtotals and totals, we don't have to start again from scratch. We can make use of our one pass through the cards, and we can make use of the very small amount of memory we need to use to keep track of this. So it's very fast. And actually, this operation could be multi-threaded as well. If you can imagine, we had 500 of these cards to sort through, and we split it up into 5 operations that could run in parallel. And operation 1 looks at the first 100 cards. Operation 2 simultaneously looks at the second 100 cards, and operation 3 looks at the third set of cards. They can flick through, and there's no need to sort the order. They can do one pass, and then each operation arrives back with a single value. So there's just needs enough memory to store an accumulating number for each operation. And then the very last task is just to add the 5 numbers together, the results of the 5 multi-threaded approaches. So there's a lot to be said. Well, there's a lot to, well, you can hopefully understand why some calculations can be very, very fast. So let's have a look at another common calculation type, the max calculation over the same sets of cards. So I want to understand, what is the highest value card in the same set of 5 cards. So we can bring the first card down, and we allocate a piece of memory that says, I'm the first card, so I'm going to say I am the highest card in my set. We can then look at the next card. We throw away the first card, the 5, and we look at the next card, and we just do a comparison. Am I higher or not? No, I'm not. So we just simply discard the value. Then we bring down the third card, and the third card we test again. Is the value of 9 higher than what we previously have stored 5? This time it's true. So we can update our piece of memory from 5 to 9. And it doesn't matter what we previously had. We don't have to keep track of history or anything like that. And when we discard the 9, we bring down the 7, the next card. Are we higher? No, we're not. No change. Then we bring down the 5. Again, are we higher? No, we're not. So we can arrive at a max calculation, again, simply by doing only a single pass through the cards. There was no need to do any sorting. We still only need to increment a single value, like with the sum calculation. There's no need to keep track of the number of cards read. Again, we can derive subtotals and totals very easily without having to go back to the set of cards and do another scan through them. And like the sum operation, this could be split up. So, you know, if we were to do this over 500 cards, we could split that up into 5 operations. Each operation arrives at its max, and then we can do a quick, simple test over the output of those 5 operations to figure out very easily and quickly what is the highest number in the set. So it can complete its operation very efficiently, as you can see. Now, a slightly more complicated calculation type is the average calculation. So if we want to understand what is the average value for the 5 cards we've randomly picked, what we're going to need to do is now keep track of 2 values. So the first value we're going to keep track of here is the 5. And that's going to be the sum total. And the second value we're going to keep track over here is how many cards have we run through. So at the moment, 5 divided by 1 equals 5. So far our average, if we wanted to complete this right now, is 5. Then we draw on the next card. So the 3 value increments our sum-like operation, but we now also keep track of how many cards we've scanned through. And if we go through the 3rd, 4th, and 5th number, we can see that our sum total is 5. We read 5 cards. Sorry, our sum total is 29, and we read 5 cards. So our result is going to be a whatever it is, 29 divided by 5, which is a relatively cheap operation at the end of the scanning of the cards. So we only need to do 1 pass through the cards, which is a good thing. We didn't need to sort the cards again, so that's quite helpful to know. This operation again could be multi-threaded. Would use slightly more memory. The downside, and this is not really much of a downside, is that we needed to increment 2 values or keep track of two values, and this is memory. And also, you know, we needed to keep track of the number of cards read, which is not really a downside. So I would still classify the average calculation in the same bucket as max and sum. Now, many of the other calculation types like min and the other ones have the same sort of profile. They can be completed very efficiently without needing to use much memory, doing a quick scan through the data, the cards, and you know, it's not too hard or heavy on the system. But now let's have a look to see what we need to do with a distinct count calculation. And this is not necessarily specific to Power BI. This is the same for any BI tool, you know, Microsoft or not. So with a distinct count calculation, say that very quickly 5 times. Let's figure out what needs to happen so that we can arrive at the correct result for this very small data set. So first of all, we need to look at the first card. So we'll bring down that and we can see that this is a 5 of clubs. But we can't throw this away anymore. What we need to do is park it somewhere. We can't discard this card. And the reason why is because when we draw on the next card, what we need to do is check to see whether we've seen this card, yes or no, before. And at the moment, we haven't seen it. And we're quite lucky that we only have 1 card to check. But we now need to park this card. And as you can see here, memory is starting to increase. Just, you know, I know this is only two cards, but just imagine this is over a much larger data set. So let's draw the 3rd card. And what we need to do, we can see that the 3rd card is the 9 of clubs. We need to go back and check, have we seen this card before? Is this a new distinct count value, or is it something that we can disregard? And no, we haven't seen this card before, so we have to park it somewhere. So we're starting to use a bit more memory here. Look at the 4th card, 7 of hearts, same story. We're going to go park that over here. We're really starting to run out of memory. This is a machine that doesn't have much memory, obviously, with only 4 cards. Finally, the good news is we bring down a card that we have seen before. Okay, so finally what we can do is, after scanning these, and perhaps we look at the first one and go, yep, we've seen this before, we can very quickly discard this. But hey, if this was the 7 of hearts, we have to check here, 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 and we can throw that away. And now that we have scanned through the cards, we can then do a count operation on the on what we've stored to arrive at our number. Now, the good the good part of this is this can be completed with a single pass through the cards. So that's a tick. So we're happy with that. With this approach, there is no need to sort, but we do need to keep track of all groups of previous cards. So if you can imagine that you're performing a distinct count over the number of customers that have visited your store over the entire year, and this is a very busy store with lots of customers, and if that number is getting into the millions of people, then anytime you want to do a distinct count operation, it's going to have to do chew up a lot of memory, but also as it scans through, it's also going to have to do a lot of checking, and that's going to start burning CPU cycles. So each card needs to check if it's new. Now this is an interesting point. Subtotals and grand totals. Now, unlike the previous calculation types that we spent time having a look at, you can't quickly derive what would be this distinct count of a value at a higher level in the hierarchy. And I've got a little bit of an example very shortly on the next slide that will walk us through that. So we will spend some time on that. And then finally, this is not an operation that can be easily multi-threaded. You know, put an asterisk there saying it can't be multi-threaded. Yes, you possibly can, but it's not going to be to the same way that you get the benefit out of multi-threading the sum, max, and average calculations. You know, because each operation, if you had 500 randomly sorted cards and you split them into blocks of 100, they still need to check amongst themselves, and they have to check what the other cards, the other operations have seen, because they might be unique or they may not be unique. So so it could be multi-threaded, but nowhere near as efficiently as the other calculation types. So let's have a look at subtotals and totals. Why is this a challenge, and why can't we derive subtotals and totals when it comes to the distinct count calculation? So what we'll do is we'll consider customers that have visited your store, and we want to understand for a given day, how many distinct customers did you see? And then at the end of the week, how many distinct customers can you see? So if we imagine that on Monday, we have 3 people physically arrive at the store. We have Bin, Nat, and then Bin comes back. Bin really likes what they bought, and they came back and they brought some more items. And so we have a distinct count for Monday of 2. And then on Tuesday, what we have is Addie, Bin, Ash, and Addie again. Addie quite liked what they bought in the morning and came back in the afternoon. So we have for Tuesday, we have 3 distinct customers that arrived in the store on Tuesday. Wednesday, there were just 2 customers. It was a quiet day. Thursday, we saw Vic new as a new customer. We saw Nat again, Addie, and Bin. So we had 4 distinct customers, which matches actually the number of customers that particular day. And then finally on Friday, we saw Ash, Vic, and Vic. Vic came twice. They forgot what they came for, and they once they were out of the store, they came back in and they got what they needed. So if this was a sum operation, we could very quickly just take these numbers here and add them up and arrive at a total. But we can't do that with distinct count because, you know, Ash and Vic Ash has come on different days and Vic has come on different days. So what is the actual total here? And off the top of my head, I think it's 5. So for every given day, to arrive at the value of 2, the engine needs to go through the exercise we walked through with the playing cards to do a scan of all the values for Monday. Then it has to start again and do a scan of all the values that match Tuesday. Then it has to start again and do a scan of all the values that match Wednesday. Fortunately, it's not too many cards. But when it comes to the subtotal or the total, it can't shortcut, can't take advantage of the scanning that we've previously already completed. We have to go back and start again and scan through all of these cards and see, has Bin been here before? Has Nat been here before? Has Bin been here before? And then, it starts to get it quickly becomes an expensive and complex operation. So hopefully that gives you a little bit of a sense as to the difference between distinct count and the other calculations and what it needs to do under the covers, what needs to take place for it to arrive at the correct value. And it's definitely an awful lot more that needs to go on. And that's why often if you are using distinct count in one of your visuals or in your report page, that particular page might be one of the slower ones on your in your Power BI report. So what can we do? And this is going to look at Power BI approaches, and we're going to be talking the DAX language here. There's a number of different ways that you can write a distinct count-like equation. So the first and most common, and probably the most recommended approach that you should use, is to use the distinct count function. So this is a built-in function inside DAX, and you just simply pass it a column. And when you do that, the distinct count will take a certain approach to arrive at a number, which happens to be the distinct count value for that of values in that column. And this would be your starting point. However, there's quite a clever and alternative technique using the SUMX iterator DAX function. And what the SUMX function does is you pass it a column using another function, which will effectively group the values in the column. And then the second value, which is the expression, or the second parameter, which is the DAX expression, is just a single value. So what SUMX does is, and if you're familiar with iterator functions in DAX, the first parameter is always a table, and in this case it's going to be provided a single column table. The SUMX table will iterate or perform as many loops as there are rows in this table, and the distinct function will provide a table of unique values, and SUMX at the end of the day just does a nice quick easy count. Both of these calculations should arrive at the same value, but they take very different approaches underneath the covers, and they suit different data scenarios, which I'll hopefully explain nice and clearly in my demos that I have shortly. So another DAX approach that I have seen is to use the count rows function and do something similar, like count the number of rows of the distinct table column. What you probably find is, if you look at this particular approach and study the logical and physical plans that get generated, is you'll find that the DAX engine is smart enough to rewrite this approach to effectively produce the same query plans that would be generated if you were to use this approach. So 99% of the time, that's what will happen. So there should be no difference in terms of, well, there should be very little difference in terms of performance if you were to use this count rows approach versus this. I just want to mention it because I do see this approach from time to time, and I think if you're going to use this, you are probably better off using distinct count, and because it's simpler, it's easy, it's more readable, and I would only really alternate between distinct count and SUMX as approaches. And then finally, there's a very interesting DAX function called approximated distinct count, where you pass it a column. And I am going to spend some time on this a little bit later on. But the idea of approximate distinct count is to apply a very smart mathematical set of shortcuts to the data, and it's a very clever algorithm that can not use anywhere near as much memory, and it can arrive at a number which is very close to the precise number. It's not guaranteed to be the precise number. It's typically within plus or minus 2%. And in some scenarios, that's perfectly fine. You know, if you're using this for a financial report that needs to be accurate to the cent for every single value in every single cell, it's not, you know, you would not use this technique. And another thing about this particular technique is that it doesn't do any work inside DAX or inside the VertiPack engine. The only time this function will work is if you're using a direct query data source, and that direct query data source is a relatively recent version of SQL Server, whether it's Azure SQL DB, DW, and possibly SSMS 2019. I would have to check that. But you have to be in direct query mode, and what this should do is push the effort down to the data source, and the data source will arrive at a value much quicker than if it was using a specific distinct count approach, and that number should come back faster, and that number should be very close to the number that the other three functions would have produced, but yeah, not using too much memory. And I'm going to show you an example of approximate distinct count, how you could build it yourself in inside the Vertipack engine, and we're using imported data and imported tables index, which is quite neat. So let's have a look at some demos. So I'm going to show you I have a Power BI model here, a very simple Power BI model, nice star schema, and my model has a sales table, which has got the transactions that I want to run some calculations over. All of these calculations that I'm going to show you are distinct count type calculations. And my nice simple model that we're going to use for the demo has a date dimension, a store dimension, or let's imagine a geography dimension, and a product dimension. So this is quite a common pattern for retail-like data models. I don't have any reports. We're going to do all the work in DAX Studio, and that's because DAX Studio has got some really great features that we can take advantage of to see what's going on under the covers when we run a calculation. You know, how efficient is it? You know, what's it doing? How long is it taking, and why is it taking that long? So the first calculation we're going to have a look at is the first DAX pattern that I recommended. So we talked about using the distinct count function here, and this particular piece of DAX is going to perform a group by the various store types, and we have 4 store types. There's store, online, catalog, and reseller, and the number of buckets that you group into is very important, or can determine which approach is probably going to be more efficient for you. And we're really only going to be comparing the distinct count approach and the SumX approach. So we're going to be grouping by store type. And then we're going to have a column called distinct count. And here is the DAX expression. What we're going to do is we're going to be generating a distinct count over the sales key column. And let's go and have a look at the sales key column, because this is important to understand. So within DAX Studio, what I'm going to do is on the Advanced tab, have a look at the metrics for the model that we connected to. We can see that there are just 4 tables here, fact, sales, and the 3 dim tables. My fact table has nearly 3.5 million rows in it. And if I expand this and have a look at the columns in this, the sales key column, in terms of cardinality or unique values, is exactly the same number of unique values as there are rows in the column. So this is like an ID column. Probably not the most efficient type of column to have in your data model, but that's a subject for another session. But let's imagine that we wanted to run a calculation that for every type of store, how many distinct sales key values have we got? So this is going to give us a big number, and it's going to be, you know, a lot more than, if you could imagine this with the playing cards, it's going to be quite high. So let's run this to see. And if I turn on my server timings, I'll turn it off and I'll turn it on again just to make sure it's working, because there's a couple of things we want to look at. How long does this query take to run, but also what's happening under the covers in terms of how this performs. Now, the other thing I want to have over here and show on the screen is this is the CPU, memory, and I/O profile of my Power BI data model. So when I run this query, we want to look quite carefully at what's going on in terms of effort for the CPU, effort for memory, and effort for I/O. So let's run this query. And it took not even 1.6 seconds, or no, it didn't even take even a second. So the results are here, and you can see that the numbers are very big for each grouping. And in the server timings, I'll just make this a little smaller if I can. No, I can't. Well, we don't want to do that. Here we go. So the distinct count did quite a bit of work in the storage engine, but very little work in the formula engine. And this is quite this is fundamentally one of the big differences between the 2 approaches that we're going to compare right now. So the distinct count function pushes as much work as it possibly can up to the storage engine. So that's the that's the effort to go to the data and collect the data. And while the engine is collecting the data, it can perform some functions. And in this case, it's actually been able to do quite a bit of the work for us. And it didn't use too much CPU, and it completed fairly efficiently. So I'm pretty happy with that. And I barely saw a blip on the CPU, the memory, and the I/O for this calculation. Now what I want to do is have a look at the SumX version of exactly the same calculation. So this DAX that we're seeing here is grouping by exactly the same store type, but we're using this other SumX pattern to arrive at the value. And I'll turn on my server timings because this is what we want to compare between the two. Waiting for the trace to update. Highlight this and let's run. Okay, and let's have a look at the server timings. Now, you just trust me that the results are exactly the same. But the server timing profile is quite different. So the total elapsed time was 3.1 seconds compared with, and I'm jumping back to the distinct count here, barely over half a second. The SumX version did a lot more work in the formula engine. It still only performed one scan, but it needed to scan all 3.4 million rows in our fact sales table. And actually, I'm going to jump back to the distinct count version. The distinct count version only scanned 4 rows. It was able to push the effort up to the data source and effectively get it to do the work for it by getting the data source to do the grouping and organizing, and there was very little to be done at the other end. So the SumX version scanned all 3.5 million rows of our fact sales table. It pulled them back to the formula engine and then did the rest of the work it needed to do to complete the operation back inside the formula engine. So in this case, what we have is a grouping with only 4 buckets and quite a high number that we arrived at. And in this case, I would certainly favour the distinct count version for this exact type of operation. And you might notice actually over here that the memory increased. The memory at rest was about 550 megabytes, and in running that calculation, it chewed up quite a bit more memory than the distinct count version. And I'll clear my cache, and we'll see how this. We'll run this again so you can see. Clearing cache brings the memory of analysis services back to where it wants to sit at rest. And what I'll do now is run the calculation. And we can see memory jumping up, it's peaking and coming back. So I had to go and get a bit of data, and we're seeing a very similar total elapsed time and a very similar profile between how much effort was spent in the storage engine versus the formula engine. Cool. So I'm going to go clear my cache back and put this back to rest. Now for my second example, this is going to flip. So this is going to show you the difference where the SumX approach outperforms the distinct count approach. So let's go and have a look to see an example of that. So if we jump back to the distinct count version, and we'll scroll down to another calculation. If I zoom out a little bit. All right. So this is a little more advanced and a little more complicated. So what we're doing here is we're grouping by every single specific date in this model. And if we jump to our analytics metrics, we can see how many days have we got in this model. We have 2,556 days in this model. It's a good number to remember. Cool. So we're grouping by individual days, and then for every single day, what we're doing is we're performing a calculation. We're going to perform a distinct calculation. So this line 14 is what we're going to substitute with the SumX approach when we rerun this. And actually, I'm going to kick this off because this does take a little while to run, and then I'll explain what's happening. And you'll notice over here in my memory is climbing. My memory is going up and up and up, and my CPU is very busy, and my I/O is going nuts in a way that we haven't seen this before. So just imagine this is on your server that you're running Power BI on. You have a published report, and you have 20 users all doing this calculation at the same time. And this is going to very, very quickly ramp up. And we're up to 29 seconds here. So what are we doing for every single day? What we're doing is for every single given day, we're going to look back 3 days. We're going to have a bit of a rolling window, and we're just going to count the distinct values of the sales amount column. And we're going to produce a result. So we should have 2,500 rows here. So every single given day will show what is the distinct count of sales amount values, for a rolling 3-day period relative to that day. And this is still running. Look at my memory. I'm nearly out of memory, and even my eye was going crazy. This is just madness. We finished. Wonderful. And I can glimpse down here and see that the query took over a minute. If we have a look at the server timings, I'll just zoom this back a little bit. Okay, I'm just going to park this up out of the way. Straight away, in the summary area, we can see that this query to complete performed 2,559 storage engine scans. Remember, we had 2,550 something days in the model. So it looks like when we see every single individual storage engine piece of activity, it's almost doing it for every single day, and we can click on each individual item to see what's going on. In terms of elapsed time, it took 152 seconds in parallel. It could run a lot of the storage engine activities in a multi-threaded way in parallel. It took 152 seconds of total elapsed time to complete this, and that's quite a lot. And the formula engine, not as much, but it sort of had to sew these things back together at the end. But pushing this activity, this calculation up into the storage engine, has really forced it to do an awful lot of work using the distinct count approach. And the total elapsed time, as you can see here, was 65 seconds, which was a minute over. So what we should do is we should clear this cache now and have a look at exactly the same calculation, but we're only going to change line 14, nothing else. Everything else will remain exactly the same. And if we look at the results, the first result was 2175, 3273. So we can just check that we're getting the same results. So if we look at the SumX version of this calculation, and if I scroll down, and make this a better size. Cool. All right, so here, in place of using the distinct count function on line 19, it's a different line number because I've spaced this out a little slightly differently. All the rest is exactly the same. I'm going to clear the cache so that we can see our memory profile get back to our baseline. I'll just let that wait for a little bit. And I'm going to kick this off, run, and 1, 2, 3, 4, and it's complete. It's complete in 4 seconds. It didn't use anywhere near as much memory. There was a slight peak. It came back. This is quite a similar profile to what we saw with the earlier calculation. The amount of effort that it put into the storage engine was lightweight. It went and grabbed just what it kind of needed. Then it did the rest of the work in the storage engine, in the formula engine, once all the storage engine work is completed, for a total elapsed time of 4.3 seconds. Now that compares to 65 seconds, and off the top of my head, doing the maths there, 65 about 15 times faster. That's pretty good. But importantly, and we're losing this off the screen, there was very little effort on the CPU. So if this is running in a heavy system with lots of concurrent users, it's not going to chew up anywhere near as much memory as the distinct count pattern. And we didn't even see any I/O. And just to double check that that wasn't a fluke, I'm going to clear the cache, and I'm going to run this calculation again. And it should take about the same amount of time. 4.3 seconds, exactly the same profile here in the server timings, the storage engine, formula engine. And we only completed 4 storage engine scans as opposed to over 2,500. And the results, 2175, 3273, 2175, 3273 as a spot check. So you can see the difference in the two. Now, I'm not saying that you should always use SumX. My recommendation is that you always start with distinct count and then consider using SumX when distinct count seems to be using a lot of memory and using a lot of time. And the reason why the SumX is performing more efficiently in this particular case is because we've got a lot more groups. The number's a lot smaller. So the number of iterations that the SumX needs to complete is much fewer. Whereas if SumX has to iterate over the table in its first parameter over many millions of rows, then it's going to quickly become less efficient than the distinct count. But it's good to know that you have options. I can park this now, I think. Hopefully that seeing the memory was useful. So what other options do we have when it comes to working with distinct count in Power BI reports? We can use pre-calculated tables. Now that you do need to put an awful lot of care if you were to try and pre-calculate tables out into the source. And what do I mean by pre-calculating tables? It's making sure that a table only has one row per distinct item, so that when the table appears in the model, you're not actually using a distinct count or an alternative to distinct count. What you're doing is just simply counting the rows in that table. But what you find is that you end up with an awful lot of tables. So this is a very edge case type solution that you might go to for a report where the distinct count was absolutely critical that it needed to be fast, and it was critical that it needed to be accurate. It will require a lot of management, and it will require a lot of setup. It will work, but I wouldn't necessarily go to pre-calculated tables as my first approach if I was just throwing distinct count in because I know I needed it. And the other option is to use the approximate distinct count, which we touched on before. So let's have a look a little bit more at approximate distinct count. What you'll find is that most approximated distinct count type algorithms around, and whatever the engine or database that you're working with, will use a variation on what we call hyperlog log or hyperlog log plus. It's often referred to as HLL. For Power BI, as I mentioned, the approximated distinct count DAX function is designed and will only work if you're running in a direct query mode and the data source that you're connecting to is a Azure SQL or Azure SQL DW, and maybe a newish version of SQL DB. But you are pushing the effort and the workload up. It won't put any effort onto your AS engine. It's just passing it to the data source. And then depending on how tuned your data source is and how scaled up it is, it'll take it that long to return the result, but I guarantee it'll be significantly faster than if you were to push up to the same direct query source an actual distinct count query, which is quite possible. Now, the other alternative is to maybe roll your own. And I did I wrote a blog post on this around this time last year. I will post those details in the chat window or the follow-up area for this session. But if you do search on my blog, which is dax.tips, dax.tips, I apologize for my accent. It can be quite hard to follow sometimes, especially when I speak quickly. But the idea is it's based on exactly the same HLL plus type algorithm that you see in the big search engines and very, very large companies use internally on huge data sets. The algorithm doesn't take the same approach that I demonstrated using the playing cards. What the algorithm does is quite cleverly creates buckets of values and then uses those values with harmonic mean, and which is like a bit of an average, and then an average of averages to help arrive at an accurate number, but with a few tricks along the way. And I'm not going to delve into the line-by-line nuances of HLL. I guarantee, if you are interested, and I found this very fascinating myself, is just do an internet search on HLL+. There are many good papers around that describe exactly how it works, why it works. They will often give you a pseudo formula version of the algorithm, and that's what I used to come up with a DAX-based version of this. It uses a lot less memory. It's clearly faster. And the accuracy is surprisingly good. And I've got some demos of, I've got some examples which I'll show you now, just how accurate that is. So, and these snapshots are from my blog. So if you're interested in, I have a lot more detail explaining which each query, what each query did. But this result set that you're seeing here shows that I had 5 different types of queries, and each query had a different data profile, similar to the 2 data profiles that we've just used in our demos earlier, where they're either grouping by a small number of values but calculating over a large number of distinct value items, or having a large set of groupings, and the end results are generally smaller. But what I found was that for query 1, which was my best query, when I used a precise distinct count calculation, if I can zoom in here. Cool, yeah. Oh, I might just move that off and zoom in again. Cool. So query 1, the precise distinct count calculation took 173 seconds. The HLL version over exactly the same amount of data only took 6.6 seconds. So it was 25x faster, which is pretty good. The next query, it took 133 seconds. The HLL version took 10 seconds, so it was only 13 times faster. The slowest version, and there's a lot more detail in my blog, but it was still pretty good. The non-HLL version took 85 seconds, whereas the HLL version took 37 seconds. Now, all of this data was computed inside the analysis services engine. What I did was I think from memory, I brought in about 50 billion rows of telemetry data. This was actual real-life production telemetry data from Microsoft that had been anonymized before I got my hands on it. So I could do calculations like, just give me the distinct count of user IDs that have used this particular product over a large period, like over the entire 2 years. That sort of describes query 1. And not only was the speed impressive, the 25x gain, 173 seconds down to 6. If I was to show you the exact same memory profile that we used when I was doing the demos in DAX Studio just earlier, the precise distinct count would just ramp straight up, chewed up all the memory on the box. And if anyone else was trying to be active on that box at around the same time, they were pretty much out of luck. And then when you ran the HLL version, there was very little memory was used. And so if other people were busy doing their sum x's and averages and means, they barely even noticed that you were hogging the machine. But certainly on the distinct count, the time taken on the milliseconds is not the only story. It's how much of the other resources on the server are being chewed up. So this was 50 billion rows of data, and it was pretty cool. Again, the detail is in my blog. Please go and feel free to go and have a bit of a look at that if you're interested in seeing exactly how to put it together. And my blog gives you the instructions and the source code, how to write the SQL, how to set it all up, and what the DAX looks like. And I've had quite a few people have fed back to me after reading the blog to say, without any other help, they were able to set it up, and yes, they saw similar gains on their very large data sets, and the larger the data set, the better it works. In terms of accuracy, so what we're looking at for accuracy of here is the accuracy of the numbers for query 1. So the actual precise value for the distinct count value that took 173 seconds to produce, here was the number that it generated for 2019, 2018, 2017. Remember I said this was telemetry over 2 years. Now the HLL version came up with a number that wasn't exactly the same, but look at it, 143 million, 13,626. 143 million to 143 million. We're in the right ballpark. And in fact, we're only less than a million out, 0.67%, less than a percent out. The other two values for 2018 and 2017, we were only 52,000 out and 23,000 out. It was incredibly accurate. So the number that the HLL version produced, which is important, was still good enough, for some applications, for some use cases. So you can see how accurate HLL can be with these queries. And then finally, the engine number. So for query 1, which is focusing on here, I ran it 3 times, excuse me, and for each time it ran, the amount of storage engine that was taken up, and just imagine that this is memory. This is my memory chart ramping up and flying through the roof is described here. And we can see the equivalent memory usage for the HLL versions across 3 runs, just to see how they went. And Formula Engine was barely even registered. So in terms of resourcing, it's quite a significant difference over, again, very large data sets. I wouldn't recommend you do this on if you're only dealing with 3.5 million rows. If your underlying data set is multiple billions, then that's when you start thinking about whether approximate distinct count is worth the effort of building into your model. Excuse me. So in summary, I think we have covered, hopefully, I've been able to explain in a good way why distinct count can be slow and why it particularly is different from many other calculation types in a Power BI model. We had a look at the main DAX patterns that you should consider when you are designing your models and you find you do have to work with a distinct count calculation. As always, with any DAX really, start with distinct count. And as always, test and benchmark. This is really important to understand the data profile, because every model is different. Cardinality is important. The shape of your model, the relationships, all of these things can come into play when the engine, when it comes time to run your query, what plan does it produce, and how does it go about completing the operation to give you the number you need. And we also looked at the approximate distinct count option as an alternative, and what its pros and cons are. In terms of references, and I'll post this document somewhere in the follow-up to the session. So there's a very good paper, as always, from the maestros over at SQL BI, Alberto and Marco, on analysing distinct count performance in DAX. So I highly recommend that as essential reading. The blog I mentioned when I talked about approximate distinct count is over here on dax.tips. Another website that I just want to give a plug to is we've recently added some free online training for DAX. This is Microsoft Learning Path. So if you want to beef up your DAX skills, particularly if you're doing an analyst type role, then I highly recommend you head over to ako.ms/learndax. There's 7 modules there that you can walk through at your own pace. You download some files and you can follow some labs, and you can create some calculations, add formulas, add measures, and it slowly gets more complicated. And hopefully that helps you improve your DAX, which is always a good thing. And lastly, I always like to give a plug out to our PBI guidance website. So the team I work with, we do learn an awful lot when we work with large customers and encounter the challenges and varied scenarios that we see. And we like to put all of our learnings in one place. And this covers what are the best practices for data modeling and DAX and a bunch of other things. So I just want to put a plug there. If you haven't seen the site, I recommend going to it. It's a live site, so we're always adding to it. And if you follow the guidance there, then you can't go wrong. So lastly, thank you for your time. Thank you for jumping on this call, whether you're watching it live or later on a recording. Please feel free to reach out to me. I'm on Twitter and LinkedIn if you have some questions or some interesting things you want to share, particularly if you're going to look at that approximate distinct count. I always like to hear if people have implemented it and what success they've had. I don't guarantee that I'll be able to answer you straight away, but I do enjoy chatting to people about DAX and Power BI, so do feel free to reach out. And lastly, just a bit of a plug to an upcoming an event later on this year, the Data Data Platform Summit 2020. Hopefully you know about it anyway, but there's a huge amount of sessions and training classes. And right now, if you go to use the discount code DPS 2020, you can get a over half off, which is a pretty good deal. There's experts from all over the world. I'm looking forward to coming along and doing a session on DAX. Maybe I'll see you there. But otherwise, that's all for me. So if we've got some of our moderators listening in for questions, now might be a good opportunity to have a look at those.
Yes. First of all, thanks a lot, Phil, for taking out time out of your busy schedule to deliver this session. As far as question, I don't think the audience have not yet posted any questions. So let's just give them 2 minutes.
Sure, no problem.
Yes, friends. So if you have any questions, please quickly put them down in Q&A panel so that Phil can answer them.
Maybe I just explained everything too well.
Haha. Yes, that sounds about perfect. Yes. And meanwhile, I will put down a couple of links. One will be the session feedback link, and another will be the event feedback link. And
cool, thank you.
Oh yeah, this is your first question, Phil.
So you have a question, sorry?
Yes, so if you can head over to the Q&A panel, Dinesh has a question. Where can I find the DAX functions?
Where can I find DAX functions? Okay, there's a couple of good websites that you can go to that give you a really good explanation of DAX functions. So I'm going to pop this up here. If we go to aka.ms/DAX is the Microsoft reference site. So what we can see here, if you go to aka.ms/DAX, you can see every single DAX function here, grouped into categories like filter functions, logical functions, other functions. We can click on an individual function and it will describe what the signature parameter that's required is. So SumX says it needs 2 parameters. They need to be a table and an expression. It describes what a table is. It tells you what the result set is. It's going to return a decimal number and a little bit of information about that. So that's the Microsoft version. Another very good one is dax.guide, which essentially does a similar type of, provides a similar service where it lists all DAX functions. You can click on them, and what I really like about the dax.guide version, which is built by the SQL BI guys over there, Marco and Alberto and their team, is they provide, often they have links to blogs, very, very detailed and useful blogs that they've written, and it tells you what the compatibility mode is. So these would probably be 2 good places that you would go to. Lastly, if you open DAX Studio, what you can see here in the tab function, if I zoom in, is there's a button there called functions, or a tab there called functions, and if I click on that, we can see all the DAX functions, but it doesn't necessarily give you the same help. You can just double click on the function and it tells you the name and the signature parameter. So I personally would use the websites first as my go-to areas. Either one would be fine, and but otherwise, if you want to quickly see the DAX functions, then if you're not using DAX Studio already, I recommend it, and you'll be able to see them there. So hopefully that answers your question. And in fact, on the Microsoft version, we do have a small section for what are the new functions, because DAX is a live language. We're always adding functions, and you can see we added a whole bunch of functions just as recently as July this year, and going back beyond July, there's a couple of DAX functions that have been also added this year, or nearly this year. So this is another good place to keep your eye on. So thank you for that question. That was very good. Dinesh says, "Thank you so much thank you, Dinesh, for coming along. I hope this was helpful, and it means that if you are using distinct count in your Power BI models, you've got you can make it run faster for your end users."
Yes, I don't see any more questions. If there are any questions post the event, I'll make sure that it is forwarded to you. Okay, there's one more question from Dinesh.
I can see it says one more question.
Yeah. And meanwhile, friends, I've given you the links in the chat window. Please use them to give your feedback. Thank you.
in Power BI, can we create forms? Now, I'm guessing, Dinesh, you mean a form such as the providing the end user with the ability to type in data, such as a name or type something in. I would probably say, without understanding deeply your requirement, that the Power App visual would give you the ability to create quite rich and detailed forms to allow your end user to type in a wide variety of content. But you would connect that Power App back to an underlying data source that maybe Power BI was direct querying over. Otherwise, if it's just a case of selecting a geography or selecting a product grouping, etc., you would normally use just slices and filtering. But because you use the term form, I suspect you mean allowing the end user to key in data. There is a Power App visual for Power BI, which you can embed into your reports, that gives your end user the ability to key stuff in and write back, and then you can refresh your Power BI report to see the data that's been added. So hopefully that answers your question. It's not specifically on distinct count. Prashant asks, what is the difference between managed enterprise BI and self-service BI? That's a complicated answer, which almost deserves a whole session in its own right. But managed enterprise BI is possibly where you're talking about dedicated admin teams, BI teams, that build very large centralized models and control what goes into them in terms of data and measures, etc. And they share that. They make that available to the organization. They quite often build the reports as well, perhaps reports that go to senior executives, etc. And it's very controlled, but you can build an awful lot of trust in these systems, because quite often it's peer reviewed, and a lot of thought and effort goes into making sure the data is coming through timely and is accurate and reflects what the business understandings of the various KPIs are. Self-service BI is perhaps a little bit more Wild West is probably an unfair name, but where people can spin up their own BI tools, such as the wonderful Power BI, and ingest their own data and create reports very quickly, easily, but maybe you do have to be cautious and careful about, are they using the right data? Are they using the correct definitions for various metrics, etc.? And there's pros and cons around speed of delivery to the getting things done, because quite often managed enterprise BI, if you want a new metric or you want some new data, it can take weeks or months before the information is visible to end users connecting to their models, whereas self-service BI is very much build it yourself, control it yourself, and the time to get access to information is a lot faster. But there are higher risks involved when it comes to accuracy and errors. So that's one definition, but yeah, it does definitely deserve a session in its own right. I mean, the trend is definitely towards encouraging people to be able to build their own models much more without relying on IT so much. And there are pros and cons with both approach. So it's always good to try and extract the best value, the best out of both approaches. And it can be done. Both approaches can be done successfully and well in organizations. I've seen that. So wonderful. Well, thank you, Prashant. And again, thank you for jumping onto the session. I always enjoy talking about DAX, Power BI, and interesting topics such as distinct count and aggregations. But it looks like we might have answered all the questions there.
Yes, so I think that concludes our session 7 of today's event. Once again, thanks a lot, Phil, for taking time out of your busy schedule and delivering a wonderful session for our audience. And looking forward to see you at DPS 2020.
Absolutely. I wish I could be there in person. I did come a couple of years ago, and I'm looking forward to when I can come again. I really enjoyed Bangalore, had a great time, and absolutely coming back. So I'll see you all then in person.
Thank you. Thank you, Philip. Have a great day.
No problem. Bye-bye.